Good afternoon and welcome at the Lab Analyse Online Week. Already the last presentation for today. And we have Kurt Taxton from Gerstel, who will be doing the presentation on behalf of Vinci Laboratory Solutions. And Kurt will be talking about GCMS. Any questions that you have during his presentation, you can put in the chat. And then after his presentation, we'll have some time to answer your questions. So please, Kurt, it's all yours.
Oh, thank you. Good afternoon, everyone. Thank you for coming, particularly when there's a lot of presentations going on and a lot of things that have changed this year. And I appreciate you taking the time amongst your busy day to come listen to this one. So I'm very grateful. We're going to talk about microplastics analysis using what is essentially two different ways to do pyrolysis. One, which is more traditional, but I'm going to spend most of my time talking about a new technique that was developed by the German Institute for Material Research and Testing in Gerstel. So without any further delay, let's jump right on in. Well, first, just a quick word about microplastics. So what are they? There's no exact definition to microplastics. There's an ISO definition and an ISO method that tries to get at that plastic particles that are 1 micron to 1 millimeter in size. Everyone does generally agree that there are two kinds of microplastics. Primary, which is plastic pieces that were made small on purpose. These were commonly used in like facial scrubs to clean to get the dead skin off your face. So the abrasives that are purposely made small. And then the larger problem, though, is secondary microplastics. These come from larger pieces of plastic that fall apart in the environment through a variety of processes. So anything that's large eventually becomes small because of mechanical abrasion, and we get a lot of microplastics. So the picture gives you an idea of how challenging this is. Those are all microplastic particles. Got this from the internet. This is one particular example, but there are many. And it gives you the kind of challenge that we're up against in trying to analyze microplastics, because there's a lot of variety there. Different kinds of plastics. Thermoplastic polymers, thermoset polymers, elastomers are also included in that. So it's a wide variety of relatively high molecular weight species, things that are not by themselves good for GCMS, and consequently, nor since they're non-polar most of the time, LCMS techniques aren't great either. So some other way to go about this has to go on. And as is common for polymer analysis, it turns out that one of those ways is pyrolysis. But before I get to that, let's just talk about overall the kind of information you need for microplastics. If you want to look at, if you want to analyze microplastics, you need things like the number of particles per volume or per area. The mass concentration, you want to know like micrograms per volume or micrograms per area of how much plastic is there. Which plastics, of course. Particle sizing is important, particularly if the morphology of that, the shape of those small particles can show you that it's a primary microplastic because it was made small. So they'll have a very uniform look to them. Secondary microplastics, which are made by erosion, of course, have random shapes and sizes. And then the state of degradation. We'd like to know, we can tell by looking at things like oxidation, roughly some idea of the environment the microplastic was in, how long it's been there. Now, we like to have all this kind of information. And in the world of analytical chemistry, when you look at this information as an analytical chemist, you're thinking to yourself, wow, there's no really one way to get at any of that. You can't just produce this analyzer. I wish we could. We would gladly provide it to you, but unfortunately, ends up being, you have to look at this many different ways. One common way to do this, and it is very successful, micro FTIR or micro Raman is very good. Spectroscopies are very good at looking at microplastics. They can identify many types of plastics this way. It's non-destructive, so the sample can be analyzed by others. And the number of particles can be counted. So these are literally images taken from an article on environmental pollution. So you can actually see all that. However, it's time consuming in regard to sample prep and measurement, and it's at best semi-quantitative. There's no easy way to add all these up and look at these in a numerical fashion other than doing it manually and sorting these things out. Consequently, there's other ways of looking at microplastics. The spectroscopic ones are valuable, but we're going to spend time talking today about thermoanalytical methods, pyrolysis, and this new technique called thermal extraction desorption. Are other ways of doing this. Spectroscopic techniques are great in giving you particle sizing, number of particles, the morphology, obviously, if you're seeing it under a microscope. But they can't give you mass balance. They can't give you an idea of micrograms per volume or micrograms per area of what's present in that microplastic sample. And this is something that pyrolysis can do. So you can also get the type of polymer. With pyrolysis, you can get an idea of some oxidation products, but you can't get particle size or number, but we can get the mass balance. And the mass balance is very important. It's one of the key things you need to know in terms of understanding how the impact of microplastics on living creatures, because in the end, you want to know as a person, for example, if I'm drinking water out of a bottled water, how much mass per volume polyethylene is going to come in with that and is going to reach my body. So that mass balance number is a focus of R&D and research, and that was one of the things that was worked on in Germany as a way to try to understand the best way to get the mass balance information. So pyrolysis does a good job of this. If you're not familiar with pyrolysis, it's relatively simple. You take a small sample of polymer and you heat it to 600 degrees or maybe as high as 1,000, and that forces it to decompose. And when it decomposes into what are called marker peaks. There are, for example, polystyrene. If you decompose polystyrene, you'll get styrene, styrene dimer, styrene trimer. That kind of tells you that the original compound was polystyrene. So you get these marker peaks that tell you what things are. Very handy at that. And you can quantitate off of that as well. You can do quantitative pyrolysis. And it gives you some other things as well in terms of being able to look at. You can do two-step pyrolysis, for example, to try to get some of this other stuff, some of the polymer additives like BHT or phthalates. The downside to pyrolysis, and as someone who's done pyrolysis in his professional career for about 25 years, I often joke the ideal size of the ideal sample size for pyrolysis is one you can barely see. The problem with pyrolysis is that when you pyrolyze that sample, nearly all of it is going to wind up going on in the GC column. So if you think about that, ask yourself if you would be comfortable putting, a microgram of pure solid into a GCMS. It's an instrument that's used to looking at things in the nanogram, femtogram range. It's very easy to overload a GCMS, and thus the sample sizes for pyrolysis are very small. If you're collecting, let's say you're going to take street water and run it through a filter to collect these microplastic particles. That means if you want to understand, the filter might be fairly large, or even on a filter like this, it's about the size of a coin. You're going to have, for pyrolysis to work, you're going to have to take several samples across that filter to make sure that you've got something representative. So though pyrolysis works for one sample, to get a representative analysis of a filter paper, it might take 10 runs or more to be able to understand that. And that really increases the amount of data you have to look at. And that was the problem that researchers were running into. Was pyrolysis works great, but there's a lot of work that has to go behind that, and it ends up being too much work on the data analysis side. The ideal way to solve that problem would be able to pyrolyze larger samples and get this mass balance information from markers, but not put all that stuff in the GCMS if you can. So you want a very, it's kind of it's an incompatible wish. You want the largest sample you can get being run on an instrument that is sensitive in the femtogram range. So you've got to find a way to make that. How do you make those two things balance themselves out. And that's indeed how thermal extraction desorption came about as a new way to go about this analysis. And this is what a TED system looks like. It's a combination of a thermogravimetric analyzer, in this case a Mettler-Toledo TGA2, sitting next to a Gerstel thermal desorption system on top of an Agilent GCMS with automation that runs actually between the two systems, as you can see in the picture. So that's what the overall system looks like. Let me go through the bits and pieces that make it up. So it's two steps. The way we make large samples work for microplastics, we break up the process into two parts. We do all the decomposition in the TGA. And by the way, I'm not going to show any of it. I'm not an expert in TGA analysis. One of the great things you get out of TED is you get TGA data about these polymers as well. So we've got the TGA data that goes hand in hand with what you're going to see in a bit as the GCMS data. We're going to use the TGA furnace to do the decomposition. And we're going to, as you can see in this picture, there is a in red, we're going to put a piece of PDMS, polydimethyl siloxane, in there on a Gerstel twister. Most of the effluent from the TGA furnace is going to flow around that twister and not be collected on it directly. And that's how we solve this problem. Most of what gets pyrolyzed is never going to be collected. Remember, all we're really after is the marker compounds, and we need enough of them to be quantitative, and that's the magic. So we pyrolyze the sample in the TGA. We collect some of the effluent on a PDMS trap or twister. That's the first step. Once that step is complete, in the next step, the robot picks up that sample, moves it to a GCMS, heats that PDMS back up to about 300 degrees, and all the marker compounds come off of it and are going into a GCMS for separation and quantitation. I might add, and this is one of the beauties of this, that as a pyrolysis person, I'm really jealous of. While this step is going on, one thing you can do on the TGA while it's not running a sample, you can have the TGA heat itself back up to 1,000 degrees in pure oxygen. Something you can't do on a GCMS system. Obviously, oxygen is a problem for GCMS. TGA doesn't have a problem with that. And in 1,000 degrees in pure oxygen, you will scrub the entire TGA out, and you'll be clean and ready for the next sample. And that's an amazing convenience about this system that unfortunately I don't have. It isn't talked about as much as it should be. So let me put it that way. But if you do pyrolysis, you can understand the power of this. So it's a two-step process: pyrolyze in one and analyze in the other. So breaking down what all these are, and going from the top to the bottom is a Mettler-Toledo TGA2, and that's the white box on the right. This is in the upper picture on the right. That's the Mettler-Toledo. Next to it's a Gerstel TED TGA interface. That's if you look at the lower picture, this thing here is a TGA interface that's sitting on the TGA, and that's off in the upper picture. You can just see it off to the left there between the TGA and the GCMS. It's just that little bit right there. So on top of that interface is a Gerstel TDU2, or if you want a larger Gerstel TDU.5 that's placed on there. There's Gerstel twisters inside that when it's running. They're not shown in the picture because they're inside. And then on the left, in the upper picture on the left, this is a classic Agilent 8890 5977B GCMS. On top of it is also a Gerstel TD. And between the two is this MPS robotic that actually ferries samples between the two of these. Being able to run the samples between the two is a huge convenience. It allows you to automate the full process of analysis. However, if you have a TGA in your lab that's in a separate room from your GCMS, it's also possible to pyrolyze the samples in the TGA, collect them onto PDMS twisters, and then pick them up in a tray and move them yourself to the other room. So the connection between the two is not absolutely necessary, but it's awfully convenient, particularly if you're running a whole lot of samples. So looking at this in detail, here's how this works. In the first step, we're going to pyrolyze in TGA. So we're going to take an environmental sample. This could be sediment, soil, sand. If you're looking at drinking water, you would have run the sample through a filter. So now you've got a solid sample that you're going to put in there. Remember, that's going to have all kinds of stuff in it. Drinking water samples, everyone likes to do drinking water and talk about polyethylene in drinking water or polyethylene terephthalate. Great example, but it's the easiest one. The real test comes in looking at sewage sludge, which you'll see some slides of that later in this. The nice thing about TED, because it's using the Meltler TGA2, we can have a sample size up to 200 milligrams. That's huge. And that allows us to do very large samples. But again, because of the magic of the way this works, we're not going to put 200 milligrams onto the system. And then we pyrolyze in the TGA. So that goes on. The TGA heats up to usually around 600 degrees, and we're going to collect what comes off. This is from a microplastic sample. This is the only TGA data I'm going to show today. This is the example of some of the TGA mass change data as the sample gets heated up in the TGA. And then as this pyrolysis process goes on, we're going to collect this inside a glass tube that has a Gerstel twister in it. And again, we're going to collect only what we need to collect, and we'll throw away most of the rest of it, which would overload the GCMS to begin with. So, alternately, you can actually get these TGA cups now that actually have the filter screen built into them. That allows you to skip the entire process of having to do punches of filters. Now you can run water or potable water or surface water through these and collect your microplastic samples, and then run these steel cups directly. So they're stable up to 600 degrees, and they work really well for this. No other filter media is needed. So there's a misprint on this slide. It should say first step is pyrolysis, and then after that we look for the marker compounds. And I mentioned this before, polystyrene. This is styrene at mass 91. Is one of the marker compounds for polystyrene, not the only one. Polyethylene comes apart into all kinds of pieces because it unzips the polymer, and you wind up with literally about 100 peaks you could choose from. We generally go after one major peak with a couple confirming peaks. Polypropylene works similarly, just with a different pattern. So you can imagine, you'll see some more of this in a minute and some other examples. Again, I apologize for the misprint. The next step after this should be polymer identification, and we use software to go through the chromatographic and mass spectrometric data to hunt down and find these marker compounds. And we find them not just by their mass spectrum, but we also use retention time data. The software called ChromaIdent also expects, for example, for polystyrene, you have to have 3 peaks there to be called polystyrene. If the other 2 aren't there, you have styrene in your sample, which could have come from an environmental source. So it uses a lot of information, the mass spec data, the retention time data, the chromatographic data, and the chromatographic peak pattern to hunt down these polymers. And then again, my apologies for the final step, we're going to quantitate off that, take that information and quantitate these peaks. So this is an example of 8 different kinds of polymers run this way to give you an idea of what we're looking for. Polyethylene's on the top. That's one of the marker compounds for PE. Polypropylene gives you this kind of chromatographic pattern. Polystyrene, this chromatographic pattern, and so on. So we have, for a number of things, going all the way down to styrene butadiene rubber in the last example, we have marker compounds that are unique to all of these kinds of polymers. And the nice thing about this, about doing it this way, you could say, well, okay, I've got styrene here. How do I know it didn't come from the environment? Well, because we heated it, made it fall apart, and we're going to look for the other 2 compounds that prove that it's polystyrene. We're not going to use things that are naturally in the environment. We're going to use things that only happen if the polymer is unzipped. So you can't have regular contamination from semi-volatile compounds this way. The polymer is unzipped, and we're looking for decomposition products that can only happen if the original polymer were there. Very calibratable. So this is an example for polyethylene. Good correlation between spike mass of polyethylene and peak area of typical polyethylene marker compounds. Note, polyethylene, we're going to use 4 different marker compounds here. We're going to quantitate off of 1. We're going to use the other 3 as markers to prove that it's there. as you can imagine for polyethylene, you're not going to find 1,15-hexadecadiene in the environment naturally. So that proves that it's polyethylene that was there. And of course, there's the 3 other marker compounds that also prove that. So the marker compounds occur during pyrolysis. They do not occur naturally, and you can't get false. It really knocks down your chance of getting a false positive. Like I said before, you won't find these decomposition products in the natural environment. So now we're going to take our sample a little more dirty. Let's look at street sludge or street drainage. This is broken down into several samples. It was sorted out by different size filters to take the size fraction down and try to get an idea of what the makeup of the street drainage was. This goes all the way down to the sludge being particles that are smaller than 10 microns. So this is really essentially gunk, and we're still able to run that. And in that sludge, for styrene butadiene, that ends up being where most of that is. So not surprising, in street drainage, you've got a lot of SBR. Styrene butadiene rubber is the primary thing that tires are made out of. So we get these marker compounds, and again, we know it's SBR because we've got 4 different marker compounds that prove that it is. So really powerful technique. And this is not a pretty sample either, as you can imagine. The street drainage can get nasty. So getting back to comparison, pyrolysis GCMS is more simplistic. It's a single instrument, but the downside is that, again, the sample sizes are small and you end up with more runs that are needed. And there's higher risk of GCMS contamination. Again, if you run sewage sludge on a GCMS and pyrolyze all that, most of that is going to wind up on the column. So that's a problem. Compared to TED, you do need TGA and GCMS either coupled or individually. So it's more investment and more trouble to set up. But the high capacity, 20 milligrams, typically up to 200 milligrams, gives you a very representative sample. Pardon me. So you have to actually take less data. And the beauty of this, really what TED is, you can think of it as an offline pyrolyzer. We're going to pyrolyze offline the GCMS and let that handle all the muck and all the trouble and take the data that we need and move it to the GCMS. So it's cleaner and more reliable and a better way to do microplastics analysis. Polymer so getting back on this representative thing, this is a sample that's been run by both pyrolysis and TED. And don't worry about reading all the stuff about the number of marker compounds. Just visually look at the 2 chromatograms. It's pretty clear visually that the TED chromatogram has much more information in it. And that's because we could get more sample into the instrument and we get more information. For pyrolysis to get this kind of information, we would have had to have taken many more samples and added them together to get all the same information that's in one TED run. And that's when I talk about representative samples, that's really what I'm after. So pyrolysis, not enough particles for representative sample. TED, 10 times more marker peaks, more representative and much more reliable. And I mentioned it, and I had to throw it out there. Yes, you can do sewage sludge. So this was an example of sewage sludge. It was run through filtration, and this is we've identified the software is hunted down and found polypropylene in it. So there's plastic in your sewage sludge. That raises an uncomfortable question: how did it get there? And unfortunately, that means it probably came from you. Well, not you personally, but it came from us as people. Processing polypropylene. So this is why microplastics are such a hot topic in environmental chemistry right now. They're in us. We're carrying it around with us. The plastics that we love to use for all of their convenience are also inside of us, and we're not sure yet what the implications of that are. And TED is a way to try to quantitate the mass balance of all this to understand the health risks. There's a whole bunch of reference articles on this. Probably the best one is in the first one, the J. Chromat paper by Ulrika Braun and her colleagues. This is a great overview of what it was used. There's been several more since. I think there's at least 2 more up now that are not on here. There's a Gerstel and Agilent application note that is about to come out on microplastics that we'll be very happy to share with you. So there's a bunch of information out here. It's becoming an established technique. It's going through ISO right now. There's an ISO method that microplastics is being written into. Gerstel serves as part of ISO. I'm part of that process myself personally. So yeah, it's becoming a standard technique and will be widely used in microplastics going forward. So thank you for all your time and for taking your afternoon time and spending with me. I hope you enjoyed this. And if there's anything that we can do to answer any of your questions or to help you, please let us know. And I look forward to seeing all of you again soon. Thanks.
Thank you, Kurt, for your nice presentation. I see we have one question from Thomas Lucius. A bit of a sidetrack, but from my understanding, currently data from a pyrolysis is difficult to get quantified within, for example, internal standard on GC, an IS that goes through the full injection system. Due to the unpredictability of the breakdown, and there ways to improve this quantification aspect, or is this seen as the unnecessary for the quantification? Can TED GCMS circumvent this issue?
I'd like to refer you back to BAM, Ulrika Brown and her colleagues, to get a detailed answer on that. But I will share with you what I do know. Though internal standards can be used, I don't think that they're always necessary. They're actually calibrating this with external standards, and it works fine. They have reference materials, BAM does, that they actually provide that have been and are currently being used in round robin studies inside Europe to prove the validity of the method. So I guess the best answer to your question, rather than talking about the details, is to go back to the round robin, and that its quantification is successful because the round robin certification data is proving it out that way. So, but in terms of the details of how it was best worked out, I'd love to connect you with the right people.
Okay, thank you, Kurt, for your very interesting presentation. Yeah, if anybody wants to review the slides or the replay of the webinar, then we will be sending out a mail on Friday with links to the slides and the replay, so you can watch it again if you missed anything. Furthermore, I would like to share a link with you, and via this link you can register for the rest of the webinars that we have tomorrow afternoon. We still have 3 presentations left in this Lab Analyse week, so you can register for that. So if there are no further questions, and I don't see anything in the chat, then I'll be closing off this session. Thanks again, Kurt. Hope to see you another time, and have a good day. Thank you.
Thanks, everyone.
Okay. Bye-bye.
Bye.